Hey, welcome back to Calculus. We're going to wrap up section 2.8 in this video, talking about higher derivatives. So short agenda. I'm going to try to keep this one super short. So we all done with section 2.8. So what do I want to tell you about? I want to tell you about higher derivatives, and then in particular, I want to tell you about the application of it to physics. We already know about position and velocities relationship, function and its derivative. I want to tell you something about something called acceleration. Okay, so let's just get going here. Let's say we have some function y equals f of x. We'll have some specific examples here in a second, but if we just write that, and we know that in the Newtonian scheme, how we write that function's derivative, either y prime or f prime of x, yeah. In the Leibniz scheme, Leibniz writes that either dy dx or, if you like, df dx. Right, and these things are functions. We've seen lots of examples that if you start with a function of x and you take its derivative, you also get a function of x. So that new function of x, the derivative, it may have a derivative, right? So you can just sort of repeat the process. I mean, after all, differentiation is sort of like a process. You just take a function and it produces a new function. You take some function called f of x and differentiation produces something called, well, if you're a Newton fan, you like to call it f prime of x. If you're a Leibniz fan, you call it df dx. So it's a process that takes a function and makes a new function. So we can do that over again. We'll now, instead of the derivative, we're going to call this thing the first derivative. The first derivative is the function y prime. And then if you take the derivative of the derivative, you get the second derivative. In the Newton notation, you write the second derivative, well, you guessed it, y prime prime. Or f prime prime of x, the second derivative. Let's differentiate the derivative. The Leibniz notation is a little different. You kind of have to almost read it like the way it works is there's the process I was talking about. It's called d by dx, differentiation. And think of it as like you apply it to y, and it makes this derivative dy dx. So that'll help you understand the Leibniz notation, because the second derivative in the Leibniz notation means that you've applied this differential operator twice. So can you imagine you take d by dx of y, and what are you going to get? Well, up in the numerator, you'd have two d's, dd, right? And that's where we write the y. And in the denominator, you'd have a dx and a dx. And we don't treat these things like fractions, so it's written like that. All right, or if you prefer, you can write d squared f dx squared, but that's the Leibniz notation way of writing the second derivative. The two means how many derivatives you've taken, and you just kind of have to learn that that's where we write them. All right, and then you can just play this game as much as you want. You want third derivatives, okay. You write three primes, f prime prime of x, third derivative. Leibniz notation, did it make sense? You'd write d3y dx3, or d3f dx3, and so on. I could write formulas for the nth derivative. We won't really use derivatives beyond really the second in most practices, sometimes the third, but it's good to know that you can write. Certainly you can't keep just writing these primes. Eventually you're going to have to come up with some other scheme, right? Because if I wrote something like, take the prime derivative, it would take an hour just to count how many primes. So we need some better scheme than that. We can't write that for the nth derivative. So the way you write it in the Newton notation, just real quickly, is you put an n up there. That's how many derivatives you've taken. So I'm talking about the nth derivative, but you can't leave it just like that, because that would mean a multiplication of functions, or maybe even function composition. So people put some parentheses around it. So if you see a y to the n with parentheses around it, it indicates derivative, nth derivative. The Leibniz notation, you don't have to modify at all. You just write dn dxn, dnf dxn. So the n just, it can be any number. Yeah. Cool. Okay, so that's something just about higher derivatives of the notation. Now let's compute a couple, and we'll talk about some applications of them. All right, so maybe as just a real quick starter example, what if we take f of x to be, say, the squaring function? We've computed its derivative a couple of times now, so I'll just write it. It's 2x. So what about the second derivative? Second derivative, well, we got to take the limit as h goes to 0 of f prime of x plus h, sorry, minus f prime of x over h. So I'm just applying the limit definition of derivative, but I'm applying it to the derivative function. So I'm looking here. You don't have to worry about the fact that that thing's a derivative. It's no more complicated than any other function. So let's just keep going here. It's the limit as h goes to 0, f prime of x plus h. Well, that's 2 times x plus h minus 2x. That's f of x. Yeah, a little bit of algebra. Seems familiar. 2x's cancel. I'm trying to be patient. I hope my handwriting isn't too bad here, but now we can finally cancel the h that was preventing the direct substitution, and I'm just going to write that's 2. All right, so let me summarize. Got f of x is x squared, f prime of x is 2x. We've calculated before, and we just computed the second derivative, f prime prime of x, to be 2. That's a constant function. So can you tell me what the third derivative is? What's the derivative of any constant function? Did you say it? 0. Yeah, good. And then once you hit 0, the derivatives would actually be 0 for every higher derivative after that. Cool. So there's just one computation of some higher derivatives. So now let's try to keep this short. You're going to have to practice taking those things, higher derivatives. We'll get some better rules, but to keep this short, let's talk about the important application to physics. If we have a position function, I like to use the letter S for position. So it tells me where something is. Just imagine along a number line. So I've got some T number line. Sorry, not T number line, S number line. And at time t, this tells me where I'm at as a function of t. So maybe this is where s is equal to 0. So it looks like my s of t is positive right there. All right. So that's what this function, position function, tells me. Maybe it's falling object. Maybe it's an object moving along a straight line. It doesn't matter. So we know, we've talked about that the velocity, the signed kind of speed of that thing, v, I'm going to call it, but it's the first derivative. Yeah, if s of t is measured in, say, meters and t is in seconds, then this would be in meters per second, the velocity function. It's the change in position with respect to time. Derivatives are rates of change. Velocity is change in position with respect to time. Right? Positive velocity means that you're moving in the positive direction. Negative velocity means that you're moving in the negative direction. We've spoken about it. So what about the change in velocity with respect to time? It's a physics concept. It's a physics concept called acceleration. The acceleration of an object is the change in its velocity with respect to time. So I'm going to call it A, and it's v prime of t, or if you like, we can call it s prime prime of t. It's the second derivative of position, acceleration. Acceleration is the change in velocity with respect to time. All right, so again, if we put in some units, I'm going to shrink a little bit so we can see all of this at once. Let me put in some units. Let's say S is measured in meters. Everywhere T is, say, in seconds. All right, so the units on the velocity are meters per second. So what are the units on acceleration? Well, it's a derivative. So it's output units, that's meters per second, per input units, that's seconds. And you can pronounce it like that, meters per second, but a lot of people just say meters per second squared. The acceleration units are meters per second squared. All right, so I want to keep this short. I want to keep this video short. This section has been long, but just real quick, since we used something above, let's say we'll use our previous calculations. So let's suppose that we have some object whose position is t squared. Meters along some number line. T is in seconds, just like in our conversation above. So that's my position function. So at time 0, I'm at 0. At time 1, I'm at 1. At time 2, I'm at 4, and so on. I'm just moving along this number line. What's my velocity? What's my velocity? V, well, it's the derivative of position. It's 2t, and that's in meters per second. Okay, so 1 second, I'm going 2 meters per second. 2 seconds, I'm going 4 meters per second. I'm picking up speed. The velocity here is equal to the speed because it's positive. Yeah, and what about my acceleration? A of t. A of t is, well, it's the derivative of v. It's the second derivative of s. We computed that above. It's 2. Yeah, what are the units? Meters per second squared. So I have constant acceleration if I'm moving like this. Constant acceleration. Okay, we're going to talk about this application of higher derivatives a lot in this class. I'm going to leave it at that to make this video as short as possible. So thanks for listening.